In this video, I'm going to be going over the answer key for worksheet number 1 from our circular motion unit. The first thing that they asked you to do is to create a qualitative motion map in figure 1. So for this one, I just drew my velocity arrows here with the tick marks to signify that it's going at a constant speed. Notice that these these velocity arrows are changing what direction they're moving in, though, right? Here, the first one is moving straight to the right, then up and to the right, and then a little bit less up and to the right, then straight to the right again, now down and to the right, even more down and to the right, and then perfectly to the right again. Notice for my acceleration arrows then, I always have them pointed towards the center of the circle. If we pretend that there are 3 circles here, one circle on this side as it goes up the hill, one obvious circle at the very top of the hill, and then another circle on the other side. So is the car experiencing an acceleration? Yes, because it is changing direction, not necessarily changing speed. So even though it's at a constant speed, it is changing direction, so it's accelerating towards the center of the circle. Question number 3, construct a force diagram for the car when it's at the top of the hill. You should have force normal up, force gravity going down, and the force gravity should be greater than the force normal because it's accelerating down. You have force friction to the left and force push to the right. And those two are balanced because it's going at a constant speed horizontally. It's staying the same, so those two forces are balanced. Next says, suppose the speed of the car is 11.1 meters per second and the radius of curvature is 0.25 meters. Determine the magnitude of the centripetal acceleration. So in this case, we need to use our centripetal acceleration formula, 11.1 squared, because it's velocity squared, divided by radius. So 11.1 squared divided by our radius, which is 25, and that should give you 4.93 meters per second squared. So there's your centripetal acceleration. Now they're asking you if the mass of the car is 1,200 kilograms, what is the net force? Or really the way of thinking about it is, what is the centripetal force that would be required to cause this centripetal acceleration? So if you know the mass is 1,200, and you know the centripetal acceleration, which we just found in the question above, is 4.93, multiply those together. So your centripetal force is equal to your mass times your centripetal acceleration, which should be about 5,916 newtons. So now a quantitative force diagram of the car. If we know the centripetal force is 5,916 newtons down, and we know the mass of the object is 1,200, multiply 1,200 by 10, you get the force gravity is 12,000 newtons. And then if the force gravity is 12,000 newtons and the force centripetal is 5,900, that means your gravity wins by 5,916, which means our force normal then must be 6,084. Right, so you had to do 12,000 subtracted by 5,916. That tells you how much the force normal is, how much the force gravity needs to overcome, and then that what's left over is your net force or your force centripetal. So 7, at what speed would then centripetal force equal the force of gravity? So in this case, it would be force centripetal equals force gravity, so that's equal to 12,000. So you just plug your numbers in here, rearrange that equation. Force centripetal equals mass times acceleration, divide both sides by mass. So you knew your force centripetal was 12,000, then you divide that by the mass, which is 1,200. You find out that the acceleration centripetal must be 10 meters per second squared. If the radius of curvature is still 25, you know the acceleration, you know the radius, you can rearrange this equation to get velocity by itself. So you multiply both sides by radius and square root to get rid of the squared here on velocity. So you get the square root of acceleration centripetal times your radius will be equal to your velocity. your acceleration was 10. Your radius is 25. So the square root of 250, which is 15.8 if you plug it into your calculator. So what they're saying here is at a velocity of 15.8 meters per second, your force centripetal would be equal to your force gravity. This one is really tough, so please let me know if you guys have any questions on that. And please also remember you can pause the video at any point. So what happens if the car was going faster than that? That would mean the car is kind of lifting into the air. And this is what happens when you kind of not necessarily like make a huge jump, but you like go into the air a little bit with your car. That's kind of what's happening. On the back page, some pretty similar problems. Construct a force motion map. So again, my constant velocity arrows changing direction. In this case, the circles are a little bit different. I have a circle down here at the beginning of the hill, circle in the very middle of the valley, and then another circle on the other side. And that's why my arrows are always pointed towards the center of those circles. Oh, excuse me. Question number 10. In what direction is the car experiencing acceleration? Towards the center of the circle. So it's at the very bottom of the circle. It's experiencing an acceleration up, hence it starting to go up. Number 11, construct a qualitative force diagram for the car when it is at the very bottom of the hill. Force normal would be greater than our force gravity in this case at the bottom of the hill, and then our force push and force friction are equal or balanced. And again, the reason force normal is greater is because it's accelerating upwards, so normal force must overcome gravity. 12. Suppose the speed of the car is 15.6 meters per second, and the radius of curvature is 23 meters. Determine the magnitude of the centripetal acceleration. So again, for this problem, I'm just using acceleration centripetal equals velocity squared divided by radius. 15.6 squared divided by 23, you get 10.58 meters per second squared is your centripetal acceleration. Now, if the car's mass is still 1,200, what is the sum of the forces, or the net force, or really the centripetal force? So in this case, again, I'm using force centripetal equals mass times acceleration centripetal, so 1,200 times 10.58. You should get 12,696 newtons, or roughly around there. So now construct a quantitative force diagram. Same thing we did earlier, but in this case, force normal is greater than force gravity. So my force gravity would be 12,000 down. I know my force normal wins by 12,696 newtons. So therefore, my force normal going up must be 24,696 newtons. I don't know my force friction or the force push because I don't really have any information on that. So if the driver weighs 540 newtons, what is the magnitude of the upward force that the seat exerts on him? So the normal force, the force gravity is not changing here. He weighs 540, so it's just 540. We know his centripetal acceleration is the same as the car, so 10.58. I know his mass must be 54 because his force gravity is 540, so divide that by 10. His mass then is 54. 54 kilograms times the centripetal acceleration of 10.58. You get a force centripetal of 571.32. If you know the force normal wins by 571.32, and you know that the force of gravity is 540, you just add those together and you should get 1,111.32 newtons. And that's how much the car pushes up on you. The seat pushes up on you, because that's the normal force. All right. Please let me know if you guys have any questions as you go through this answer key. Please either shoot me an email or message me on Canvas. Have a good day, guys.